Now that we've explored the functionality offered by generative AI models in Vertex AI using the Vertex AI Studio, it's time to turn our attention to some code. We'll now use the Vertex AI Python SDK to work with models. We'll explore text generation, image generation, batch prediction, function calling, grounding, RAGs, and a whole lot more. But first, we need to set up our environment. Here I am on my local machine's terminal window, and I'm going to create a new directory called projects. That's where I'm going to store all of the code that I'll write. So I'm cding into the projects directory. Since we're going to be using Vertex AI's Python SDK, make sure you have Python installed. Make sure your Python 3 version is a fairly recent one. Python 3.8, 3.9, 3.10, 11, 12 all should work. I'm going to write my code using Jupyter Notebook, so make sure you have Jupyter Notebooks or Jupyter Lab installed. I have a fairly recent version of Jupyter, and this is what I'll use to run my notebooks. We are going to be exploring the APIs in Vertex AI from our local machine. Now, in order to configure credentials on our local machine, in order to be able to hit these APIs, we need to install the gcloud CLI. gcloud is the command line tool for managing and interacting with Google Cloud Platform resources. And it allows users to perform tasks such as deploying applications, managing services, and configuring settings directly from the terminal. We'll use gcloud only to set up the authentication on our local machine so that we can interact with Vertex AI APIs. For everything else, we'll just be working in Python notebooks. No matter what operating system you're using, there is a way to install gcloud. So if you're on a Linux machine, these are the instructions that you need to follow. Now, I'm working on a Mac OS, so I'll first show you how to install gcloud on Mac OS, and then I'll show you how you can install and set up gcloud on a Windows machine. So make sure you have a latest version of Python available, Python 3.8 to 3.13. That's what gcloud supports. And here are the installation steps that I'll be following in order to install gcloud on my Mac machine. If you have a Windows machine, you may want to skip over a few minutes. The first thing you need to do is select the right package to install on Mac OS. Now I have a Mac OS 64-bit machine, and it's an old Intel chip, and that's why I've selected the first package here. If you're using the new M1 or M2 Mac OS, then you'll choose the second package. If you're using an older version, a 32-bit version, choose the third package. I'm going to download this tar gzipped file to my local machine. This should now be available in my downloads folder. So I'm going to cd into downloads, and I'll run the tar command to extract this tarred and gzipped file, tar-xvzf. This will extract the contents of this tarred and zipped file into a folder within the downloads folder. You'll find a new folder called Google Cloud SDK created within the downloads folder. I'm just going to move it into my local directory so that it's not living within downloads. I'll cd into my home directory tilde, and here let's run the ls command to ensure that the folder has been successfully moved. Notice you can see the Google Cloud SDK folder. In order to set up the gcloud CLI, you'll find an install.sh file within this folder. Go ahead and run this file, and this will configure and set up gcloud. You can say yes or no here, it doesn't really matter. I hit enter to go with the default no. It'll ask you a couple of more questions. Do you want to update your path environment variable? Yes, I definitely want to update this so that I can use gcloud without specifying the complete path. It'll update my .zshrc file. This is the file corresponding to the shell that I'm using. It has detected Python 3.11. Yes, I do want to install the recommended module. So go ahead and say yes here if you see a message like this. And it has set up and installed gcloud. Next, I'll show you how you can set up gcloud on a Windows machine. Here I am on cloud.google.com/sdk/docs/install. And here you can see the installation instructions for the gcloud CLI. And if you scroll down, you'll see instructions for all operating systems and platforms. Just a note that the gcloud CLI requires Python, and the supported Python versions are Python 3.8 to 3.13. You can see that at the bottom. Now in the Windows version, if you don't have Python installed on your machine, the gcloud CLI comes bundled with Python 3. The easiest way to install gcloud is by using the Google Cloud CLI installer. Click on the link here that says Google Cloud CLI installer. This will download an exe file to your local machine, and this exe file will walk you through the steps of the installation process. Now, this should be available in your downloads folder. Here it is on mine. I'm going to double click on this and bring up the install wizard. Installation is super simple. We'll just follow through with whatever the wizard tells us to do. This is the welcome screen. Let's go to next. Here you have the agreement to using gcloud. Go ahead and hit I agree. That'll take you to the next page where you can specify whether you want this installed for a single user or for all users of your system. I've just gone with the single user here. Click on next. The next page will allow you to configure what destination you'd like to store the CLI at. Pick the destination of your choice. I've just stuck with the default. The gcloud CLI comes with a number of components. Just choose the default, that's totally fine, and click on install. At this point, you'll have kick-started the installation process. It'll walk through the process. It may take about a minute or two, but once installation is complete, you should see a screen that looks like this. Now, the last option here says run gcloud init to configure the Google Cloud CLI. We'll run gcloud init manually, so uncheck this. And that's the only change. Just click on finish and you're done with the installation. gcloud is available on your machine. Clicking on finish should automatically bring up the command prompt. You can bring up the command prompt manually if it doesn't open up. This is now at the directory where I have gcloud installed. I'm going to run gcloud -- version to confirm the installation. And if you see something on your screen showing you the current version, well, you're all set. Now, whether you're on a Windows or a Mac machine, the next thing is to run gcloud init. You don't need to specify the entire path. Since it has been configured in your path environment variable, you can simply run gcloud init directly. Now, I have previous settings configured for the gcloud CLI, and I'm going to update those settings to match the new project that I'm working on. So I'm going to say, number one, I want to reinitialize this configuration with new settings. Next, you'll be asked to authenticate yourself to the Google Cloud. Now, it turns out I have service account configured that I'd used previously, and that's why you see the service account here in this list. You can simply ignore that. I'm going to choose option 1 because I'd like to authenticate myself to the Google Cloud as cloud user at lunicorn.com. That's the account that I used to log in to Google Cloud earlier. Once I've authenticated myself as cloud user, the next thing is to select a project that we'll use. Cloud user at lunicorn.com has access to a large number of projects, but the project that we are going to be using is number 12 here, GCP-LLMs. So make sure you specify the right numeric value based on the project that you want to use in your Google Cloud console. At this point, gcloud has authenticated to the Google Cloud as your user account, and we've configured the right project for the CLI to use. In order to ensure that we have up-to-date components, run gcloud components update. Now you can choose to opt in to reporting. I'm just going to go with the default no here. I don't want to send usage statistics to Google. My components are up to date. Now, in order to ensure that the code that we are running within our notebooks is authenticated to use services on the Google Cloud, I'm going to run this command here, gcloud auth application default login. This will configure the application default credentials on my local machine. I'm going to authenticate and identify myself to Google Cloud Services as my logged in user account, cloud user at Lunicorn. Application default credentials are a mechanism in Google Cloud for automatically providing authentication credentials to applications running in supported environments. ADC allows applications to securely access Google Cloud Services without explicitly managing or embedding authentication tokens, and it leverages the credentials of the underlying environment. Because we are working in a local development environment, we are going to configure ADC to use my logged in user's credentials. If you're running in a production environment, this is not a good practice. There, you'd configure a service account with only the permissions that your application needs to run. You'll never use your logged in credentials. When you go ahead and run this command, you'll be asked to authenticate yourself as your logged in user. So I'm going to authenticate myself as cloud user at lunicorn.com, and the credentials for this will be stored in a file on my local machine. And when I run code using the Vertex AI Python SDKs, these credentials will automatically be picked up by the Python SDK. And these are the credentials that we'll use to access Google Cloud Services. In this demo, we'll install the Python SDK that we'll use to work with Vertex AI services on the Google Cloud. Google's recommended practice is that you install all of the libraries that you need to work with Vertex AI in a Python virtual environment. And that's exactly what I'm going to do. Notice that I'm in my current working directory, desktop projects. Within here, I'm going to create a subfolder called Vertex AI APIs. This is the subfolder that I'll use to run all of my notebooks. So let's cd into that subfolder. I'll be running all of my Python code from this working directory. Within my current working directory, I'm going to create a Python virtual environment. A Python virtual environment is an isolated environment that allows you to install and manage Python packages independently of the global Python installation. It helps avoid conflicts between the dependencies of different projects by creating a dedicated space for each project's specific requirements. So when we want to work with Vertex AI, that's a separate project. So I'm going to create a virtual environment named Vertex AI underscore VENV. So the command will be python 3-m venv and the name of your virtual environment, Vertex AI venv. Once you run this command, if you run an ls-l, you'll find that a new subdirectory has been created for your virtual environment. Now, if you're on a Mac machine, the way you activate this virtual environment is by running this command. Source Vertex AI underscore venv, that's the name of your virtual environment, /bin/activate. On a Windows machine, here is the command that you'll run to activate the virtual environment, Vertex AI underscore venv /scripts/activate. Activate.bat is a batch file that will activate your virtual environment. So I'm going to go ahead and run this command and notice that my prompt changes. On the left, you can see Vertex AI underscore venv indicating that I'm working within a virtual environment. If you'd like to connect your Jupyter notebook to this virtual environment, you need to install the ipykernel package. This Python package provides the Jupyter kernel for Python. It allows Jupyter Notebook or Jupyter Lab. We'll configure ipykernel with our virtual environment, allowing us to run our notebook code within this virtual environment that we have created. Make sure you're within the virtual environment as you perform these operations. I'm now going to run Jupyter kernel spec list that will list out the current Python kernels that are available for my Jupyter notebooks. Notice that the only available kernel here is the system-wide installation of Python 3. The virtual environment is not available as a kernel by default. You have to explicitly install the virtual environment as a kernel, and you do so using this command, python-m ipykernel install. I'm going to install only for the current user. That's why the --user flag is present. And I specify the name of the virtual environment, --name is equal to Vertex AI underscore venv. This command will set up the virtual environment as a kernel that's available for Jupyter notebooks to use. So now if you were to run Jupyter kernel spec list, you'll find that our virtual environment, Vertex AI underscore venv, is now present as a kernel. It's an available kernel. Earlier, we had gotten this message to upgrade our pip installation, the Python package manager. So I run pip install --upgrade pip so that I have the latest version of pip running on my local machine. This happens to be version 24.3.1 at the time of this recording. This is not really something that's needed, but I found it annoying to see that warning over and over again. That's why I went ahead and upgraded my pip installation. The main Python library that we'll use to interact with the Vertex AI generative models using Python on our local machine is this Google Cloud AI platform. This Python client library is meant to access all services on Google Cloud's AI platform. It allows us to manage datasets, train models, deploy models, make predictions, and so on. However, we'll be using those components of this package that allow us to work with Vertex AI APIs for generative models. After having successfully installed this package in our virtual environment, let's run pip show Google Cloud AI platform to verify that indeed this package has been installed. And it has. Notice that its summary says that this is the Vertex AI API client library. If you look at the requires field, you can see that it depends on a number of other packages that have also been installed. We are still running within our virtual environment. We are now ready to bring up our notebook server. Run Jupyter space notebook, and this will bring up a server running on your local machine. a window should open up with Jupyter running. If it doesn't come up automatically, simply copy paste one of the two URLs that you see here in the last two lines of the console output. And here is what the home page looks like. Now I'm going to open up a new notebook running using the Vertex AI virtual environment kernel because that's where I have my libraries installed. Observe that a new untitled notebook has been created. I'm going to open this up. I'll just make sure that I have line numbers enabled for each code cell. So I go to view and show line numbers, and I'm going to rename the notebook to have a meaningful name. Let me call this using the stk.ipynb. With this done, we are now ready to use the Python SDK to interact with Vertex AI APIs. Set up the imports that you need. Import Vertex AI, and from Vertex AI generative models, import the generative model class. The next thing you need to do is initialize a Vertex AI client for interacting with Google Cloud's Vertex AI platform. And we do this via the vertexai.init function. This takes in two bits of information, the project ID and the location. The project ID is the Google Cloud project where your resources will be managed. That's the GCP LLMs project that we've been working with so far. Location sets the regional endpoint for the Vertex AI service, and here it happens to be the US Central 1 region. All of the API calls that we make via the Python SDK here on in will use this project and this location once we run this init function. Next, I initialize the model to which we want to make our first request. I've used the latest generally available model, non-experimental model. At the time of this recording, that's Gemini 1.5 Pro 002. When you're watching this course, it's quite possible that newer models are available. Google has been developing new models at an extremely fast rate. My suggestion is head over to the model garden and find the latest model and work with that model. I call generative model, pass in the model ID to get a reference to that model. And once I have a reference to the model, let's use the freeform mode to get a response from the model. Model.generateContent is the function that you need to invoke for the freeform mode. Remember that the freeform mode is meant for one-off prompts and does not store any conversation history. So what are some catchy names for a coffee shop that focuses on organic and fair trade coffee? We'll get the response from the model and let's print out the response and see what it contains. Observe that the response contains a bunch of information. It's in the JSON format. It has the candidates field and then the content field. Observe the role that says model. This indicates that this is a response from the model and it's not text that we as users have sent. In the parts section, we have the text that contains the actual response in the markdown format. The finish reason indicates why the text generation ended, and that's because it came to the end of the text. That's why finish reason is stop. Average log probs is the average log probabilities of the tokens generated in the output sequence. That's something internal to the model, nothing that you need worry about. Notice the prompt token count, 19. That's the count of tokens in the prompt that we sent. Candidates token count, 336. That's the token count of the response. And the total token count is 355. And the model version that we used was Gemini 1.5 Pro 002. Let's extract just the text content. So you can simply say response.text and this will give you the response text in the markdown format. We've successfully made our first request to the Vertex AI APIs using the Python SDK. Now, under the hood, the Python SDK made use of our application default credentials that was configured to our logged in user account, cloud user at lunicorn.com. Cloud user is the owner of the GCP LLMs project and has complete privileges over all resources in that project. In this demo, we'll work with text generation using Vertex AI APIs. We'll generate text using freeform mode as well as the chat conversation mode. We've already worked with text generation using the Vertex AI Studio. This time around, we'll use the Python SDK. In this demo, I'll also show you how Vertex AI integrates with LangChain, and we'll install the corresponding Python libraries to work with LangChain. Now, if you've never heard of LangChain before, this is a popular open source framework designed to help developers build applications powered by large language models. such as OpenAI's GPT models or Google's Gemini models. LangChain simplifies the process of integrating LLMs into workflows by providing tools and abstractions to handle common tasks like prompting, chaining model outputs, and managing memory for multi-step interactions. Towards the end of this demo, I'll show you a few snippets of code integrating Google's Gemini models with LangChain workflows. So we'll install this LangChain Google Vertex AI and the LangChain library to enable this. After you install these libraries within your virtual environment, you may need to restart your kernel. So you may just want to restart your kernel right now to be on the safe side. Next, let's set up the imports that we need. I import Vertex AI, and from generative models, I'll import the generative model and the chat session class. The generative model allows us to send prompts in freeform mode. The chat session will allow us to use chat mode with conversation history. Next, once again, we call vertexai.init to initialize the client to work with our GCP LLMs project in the region that we have specified. I'll use the latest non-experimental model at the time of this recording, Gemini 1.5/002 for freeform mode and chat mode. Go ahead and instantiate that model using the generative model class. We'll use the model.generateContent function to send a prompt to the model. This is freeform mode with no conversation history. When you invoke the model.generateContent function with the default arguments and only the prompt, you're actually generating the response or the text in non-streaming mode. This means the model will generate the response on its end, on the server side, and once the entire response has been generated, that's when you'll get the response on the client within your Python code. And we'll take a look at the response from the model. Observe that we get the entire contents of the response in one shot. This is how non-streaming mode works. Now, we've already analyzed this response before. We know that the text field contains the actual response in markdown format. So I'm going to go ahead and print out the response text. And you can see the model has generated a sample email that follows up on the progress of the website redesign project. The one drawback of non-streaming mode is that the model's response might take a few seconds to generate, especially if the model is thinking and the user essentially sees nothing on screen for that time. Now, if you're building kind of an interactive application, you might want the response to be received in streaming mode. Streaming mode sends back responses in chunks or blocks. And the way you enable streaming mode is very straightforward. Simply call model.generateContent and notice on line 6, I pass in an additional input argument, stream is equal to true. Now, the return type here is a sequence of responses. You can see responses on line 1. And on lines 8 and 9, I iterate over the responses and print out the text of those responses. Now, when I run this code, you can see that parts of the response are streamed back to me, which means that as a user, I'm able to see a portion of the response as it's being generated. As far as the user is concerned, this gives an impression of lower latency and essentially a better user experience. Let's try this once again. Again, I use freeform mode. I call model.generateContent. And here I have a list of names for a book that I plan to write, which has fantasy elements and is set in a small village in Victorian England. And again, I'm using non-streaming mode, so the entire response is sent back to me in one go. And it has suggested some pretty interesting names. Let's try the same prompt in streaming mode. I use model.generateContent on line 4. I've specified stream is equal to true. The prompt is the same as before. I run a for loop over the responses and print out the response text. It'll be available to be in chunks. And in order to better show you how the streaming works, I'm going to sleep for 0.2 seconds after I print out each chunk. Let's see this and notice how the response is streamed back to me. I was prototyping an app that interacts with the generative AI model, and I found that users really like the streaming mode. They don't like to wait for the entire response to be generated because that can add quite a bit of latency. The generate content function is for text generation in free form mode with no conversation history. But if you want a chat session with conversation history enabled, you need to call model.startChat and instantiate a chat session. This mode is designed for interactive conversations, dynamic question answering, simulating chat-based dialogues, very useful for building chatbots, virtual assistants, or conversational interfaces. Once you instantiate a chat session, you can send messages on the chat session. These messages become part of a threaded conversation, and the model maintains context between exchanges that allow for back and forth interactions. Here I use chat session.sendMessage on line 3 to send a simple hello message to the model, and I print out the response text and it simply gives me a greeting back. Now that I've greeted the model, let me follow up with another message. This is a part of the same conversation. Tell me a fun fact about the solar system. And it responds with a fun fact. Just a heads up that we are working in non-streaming mode for chat. The model generates the entire response, only then do we receive it on the client. The model has given me a fun fact about the stars in the universe. Now I'm quite impressed and I say, oh wow, tell me more, and I send this message. Observe that by itself, this message has no context at all. This is simply a follow-up to the conversation that I had previously with the model, and the model has the right context and responds correctly. Observe that it gives me a response that responds to my exclamation of wonder. Vastness is incomprehensible, and it talks about what scientists estimate. Even though this prompt contained no context, it was part of the larger conversation that the model remembered. Now, what I'm going to do is set up an entirely different chat session. On line 1, I call model.startChat and I set up another chat session. That's the name of the variable. This new chat session knows nothing about what I've discussed with the model in the previous chat session. So when I pass in the prompt, oh wow, tell me more, and I send this message to another chat session, it has absolutely no context about what exactly I'm exclaiming or wondering at here. And you can see that in its response. Please tell me what you'd like to know more about. I need some context. Oh wow could be a reaction to anything. It does not know anything about the solar system conversation that I've had in the other chat session. Keep in mind that each chat session is a separate conversation. Just like the freeform mode, the chat mode also supports streaming responses. Here is my prompt. It's about a person named Sarah who's looking for new outdoor activities that she might enjoy. I'm going to send this message to the original chat session and notice that I pass in stream is equal to true. This parameter indicates to the model that I'd like the response to this message to be streamed to the client in chunks. And on lines 8 and 9, I iterate over the responses and print them out. You can see the responses come back in chunks, and the time to get the first response is faster than waiting for the entire text to be generated. This response was fairly short. Let me follow up with a prompt that will give us a longer response. Do you have other activities you could suggest? Maybe recommend 3 or 4 activities. Use chat session.sendMessage and print out the streaming responses. And here is the response from the model in the markdown format. Again, let me ask a follow-up question. I'm pretty social. Could you suggest some group activities? Send the message. Stream is false by default. And you can see that the entire response comes back in one go. Now, if you're working in Jupyter Notebooks, there is this very useful utility that you can use to display markdown text. Just import the markdown class from IPython display and pass the response text to the markdown class, and you'll get the nicely formatted HTML output right here within the notebook. Rather than viewing the raw markdown, here you get the actual formatted HTML, and this is far easier to read. Now let me show you one last thing about the chat session. Remember I'd mentioned that the chat session stores history. You can actually access the history of your conversation within any chat session by accessing the history variable on chat session. This will display all of the back and forth conversations that you've had with the model. Observe there is a role associated with each conversation snippet. The role of the user, that's when we said hello. The model said hello there back. Then as a user, we said, tell me a fun fact about the solar system. And then there was the model's response and so on and so forth. So if you need to access and store the conversation history within your product, you have that available. In this demo, we'll see how we can integrate the text generation API calls that we make to Gemini models with LangChain. LangChain, as we've discussed earlier, is a powerful framework designed to create applications that leverage LLMs. LangChain enables enhanced capabilities such as memory chaining tasks and integrating external tools or data sources. It simplifies the building of context aware dynamic applications for tasks like conversational AI, question answering, and complex decision making workflows. We've already installed the LangChain library and the Vertex AI integration with LangChain early on when we first started this notebook. And here I set up the import statements. Now, there are many imports here. I'll explain all of these different classes as and when we use them in our code. So go ahead and set up the imports and let's start working with LangChain. Before we work with LangChain, let me show you how you can add chat history to a chat session. Let's say you want to instantiate a chat session and you wanted to have some pre-built history, and then you want to continue the conversation with the model starting off after that historical context that you have provided. How do you set this up? That's what we have here on screen. Observe that I call model.startChat, the same function that we used to set up the chat session before, but I've passed in a history parameter. The history parameter is a list of historical back and forth between you and the model. You can see the contents of the history parameter on lines 2 through 28. You can see that this is a Python list of content objects. And there are a total of 4 content objects here on lines 3 through 18, 19 through 21, 22 through 24, and 25 through 27. This is the list of content objects that I use to specify the historical context for this Lucifer chat session that I'm initializing. Every content object represents a message in the conversation. Let's start off with the very first message on lines 3 through 18. Notice that the content object has a role and parts. The first message is sent by the user. That's a message that I am sending the model. That's why the role says user. Now, the actual message is specified in terms of part objects. The part class encapsulates individual pieces of text within a content, and the part.fromText method creates these text parts. The first message on lines 7 through 15 is basically me asking the model to play the role of a mad scientist. After setting the context on lines 8 through 11, I ask a question of the model, who are you, on line 13. The next content object on lines 19 through 21 captures the response from the model. Notice the role is model and the message says, I am a mad scientist. This is the response from the model. On lines 22 through 24, I have a follow-up message to the model. So the role is user, so it's my message. And then I ask the model, what adjectives would you use to describe yourself? And on lines 25 through 27, the model responds, so the role is model, and it specifies the adjectives eccentric, brilliant, chaotic. Once I've set up a session with this conversation history, I send an additional new message to this Lucifer chat session. What are we working on together? And I'm going to print out the response from the model. Observe that the model has taken into account the conversation history that we had specified, and it talks about our world domination plans. And it talks about 3 main components that we're using for world domination. This is, of course, stuff the model has made up, but it's playing the role of a mad scientist, exactly as I had asked it to in the conversation history. As I continue my conversation with the model, I can send more messages with follow-up questions. How are we planning to do this? And the model gives me a response. And it talks about the 3 components and how we'll plan to use this for world domination. Now let's see how we can integrate Gemini APIs with the LangChain Python SDK. LangChain provides tools and abstractions to handle common tasks like prompting, chaining model outputs, and managing memory for multi-step interactions. Chains in LangChain combine multiple LLM interactions into a coherent workflow. First, let's use some LangChain constructs to send prompts to the Gemini 1.5 Pro model. Now I've initialized a system instruction and a user instruction that's on lines 1 and 2, system message and human message respectively. I want the model to respond as somebody with first-hand experience of past and future events, and I'm curious about how Leonardo da Vinci will react to technology like smartphones. Now I set these messages up as a list, one as a system message and one as a human message on line 4. System message and human message are LangChain constructs that define the flow of interaction. System message sets the overall behavior of the assistant, and human message specifies what the user has asked. On lines 6 through 9, we initialize the Gemini 1.5 Pro model using the Chat Vertex AI class. Now, at the time of this recording, Gemini 1.5 Pro doesn't support system message directly. However, you can send the system message as the first human message by setting the convert system message to human to true. And you can see I've set that to true on line 8. So here in this example, we are using the LangChain constructs of system message and human message with Gemini, and then I call chat.generate to get the response from the model. And here is what the result looks like. There is a lot of detail here. In fact, there are multiple responses that have been generated. Let's look at the first of these responses at index position 0. So I'm going to access generations at index position 0, index into it further, and print out the text. And this is what the model has to say about DaVinci and smartphones. You can also access a bunch of metadata about the generated text in the generation info field. We have the average log probs finish reason. We've discussed those before. The content is blocked to set to false, so it was safe content. You can see the safety ratings for the content generated. Safety ratings, as we've discussed before, are evaluated across 4 categories: hate speech, dangerous content, harassment, and sexually explicit content. And this generated content has been tagged as negligible on all these counts. You can also see the tokens used in the usage metadata. The prompt token count captures the length of my prompt. Candidates token count captures the length of all of the responses generated by the model. And then we have the total token count. LangChain allows you to construct chains that combine multiple LLM interactions into a coherent workflow. For example, chains can be used to connect a language model with a database query to answer complex questions. Chains simplify tasks like multi-step reasoning, summarization, and retrieval. We've seen how to use LangChain constructs to interact with the Gemini model. Now let's set up a very simple workflow using a chain. Here is the system message and the human message. The system message asks the model to act as a Shakespearean scribe who translates modern English into Elizabethan style English with poetic flair. And the human message is what I want translated. The weather today is beautiful and I feel happy to be alive. Next, I'll set up the LangChain constructs for a workflow. I have my messages list. We have the system message first and then the human message. And then I use a prompt template to generate a prompt. This chat prompt template generates a template which converts a list of messages, that is conversation history, into a structured format that can be used to generate a response from a language model. On lines 4 through 10, we initialize the chat session using Chat Vertex AI. We specify the model name. Remember, for Gemini 1.5 Pro, you have to set convert system message to human equal to true because this model can't handle system messages yet. You can choose to explicitly specify the safety settings for the model's generation. I've only configured a value for the harm category hate speech, and I've said that I want to block low and above hate speech. By default, the safety settings are turned off. Here I've explicitly set a value for hate speech. On line 12, I've created a chain where the prompt, that is the messages that we want to send to the model, is passed directly to the chat, that is the Gemini model. The pipe operator in LangChain simplifies combining components into a pipeline. On line 14, I invoke the chain by calling chain.invoke. This executes the chain with the given input, and the input here is nothing. I've just passed in an empty pair of curly braces. Since the messages are predefined, no additional input is required in this particular case. And we should get the response from the Gemini model. Let's print out the response content, and here is the Shakespearean equivalent of the weather today is beautiful and I feel happy to be alive. Let's see another example of this same chain. I have the system message and the human message. I put these together in a Python list on line 14, and then I use the chat prompt template to get these in a form that can be sent to a chat model. The actual chain is defined on line 17, and I invoke the chain on line 19, and I print out the response from the model. And here is the Elizabethan translation for "I'm really getting late for work now." Next, let's set up a conversation chain with memory to allow context-aware interactions enabled by LangChain. So you can have multiple conversations using this chain, and it will make use of memory to keep track of previous interactions. We'll first instantiate the model using Chat Vertex AI. Make sure you set convert system message to human to true. Next, we'll make use of the chat prompt template to create a prompt template for the conversation that we're going to have with the model. The system message prompt template sets the assistant's persona and capabilities. The message placeholder with the variable name history adds a placeholder for conversational history to maintain context between interactions with the model. Instead of hard coding or predefining the entire conversation history in the template, the message placeholder allows you to inject the ongoing or prior conversation dynamically when the prompt is being executed. The human message prompt template is my current prompt. This comes from the variable input that dynamically inserts the user's input into the conversation. Next, we instantiate a conversation buffer memory which stores a history of the conversation. Notice that the memory key is history. This connects the memory to the history placeholder in the prompt. So LangChain will keep track of the conversation history, which is then injected in the message placeholder that references this history. Return messages equal to true ensures that the memory provides actual messages, not just raw text, for better context handling. The conversation chain on line 3 combines the LLM, the Chat Vertex AI, the prompt, that is the chat prompt template, and the memory, the conversation buffer memory, into a single conversational pipeline. We set verbose to true to get detailed logs of the chain execution. And finally, on lines 5 through 7, we call conversation.invoke to execute the conversation chain workflow. The input that we pass in here is the input that is the human message. That's the input that's passed on line 10 in the inset picture. Observe that the chain is invoked and you can see the response from the model talking about the Renaissance. All the text that you see here in green is the historical context before our actual prompt is sent to the model. The input in the response is the human message that you have sent the model. You can display that and see that it matches. The response field within the response gives you the output from the model. Because we dynamically accept the input for the chain, you can invoke the chain once again with a different input. And this will give you the response from the model for this new different input. What you see here in green is a part of the conversation history that has been stored in memory. In this demo, we'll see how when you're interacting with Google's model using the Python SDK, you can specify system instructions to the model. System instructions are directives provided to a language model to define its behavior, tone, role, or purpose during a session. These instructions set the context and guide the model's responses. We'll explore the system instructions that you can use for different use cases. Let's get started with our imports. We import the generative model and the chat session, and we'll convert our response from the model using Markdown to HTML format, which is much easier to read. Make sure you call vertexai.init to initialize the Vertex AI APIs with your project and location. The model that we'll use here is the latest model that's not in experimental stage. That is the Gemini 1.5 Pro 002 model. In this first example, where we use system instructions, we'll have the model take on a certain persona or a role. Observe that I instantiate the generative model, pass in the model ID, and notice the system instruction input argument. I've asked the model to play a role of a polished and formal travel assistant catering to high-end travelers. It's tasked with providing recommendations for luxury vacations, premium resorts, and exclusive travel experiences. Here's my prompt on lines 12 through 14. I need to get from New York to California for a business meeting quickly. What do you suggest? Remember, I'm asking a luxury travel agent this. I call model.generate content and pass in the prompt. Remember, the system instructions are configured for the model. And if you glance an eye over the response, you can see it suggests a private jet, charter, first class, business class, and so on. This bot is clearly a high-end travel agent. Let's instantiate a second model. You can see I've instantiated the model on lines 1 through 10, and the system instructions are on lines 3 through 9. Observe that this time around, I've asked the model to play the role of a casual and practical travel assistant, focusing on cost-saving options. So this particular assistant is meant for budget-conscious travelers. I have my prompt on lines 12 through 14. I need to get from New York to California for a business meeting quickly. What do you suggest? And if you look at the response based on the persona that I defined for the model, it's given me a bunch of budget travel options to get to California. System instructions can be specified when you're using your model in chat mode as well. Let's see how we can configure that. Now, let's say your organization has some kind of software that it delivers to customers, and you have a technical assistant chatbot. Here is how you'd set up its system instructions. You'd instantiate the generative model. Notice the system instructions on lines 3 through 10. You're a patient and approachable technical support assistant. We are looking for short, step-by-step, easy-to-follow instructions. We instantiate the chat session on line 13. And now let's have conversations with this chatbot that has taken on the role of a technical assistant. My computer is not connecting to the internet. This is the prompt that I sent the chat session. And here is the response. Observe that it gives me a bunch of easy things I could try out, whether the Wi-Fi or Ethernet cable is physically plugged in. Make sure the Wi-Fi is turned on, restart your modem and router, and a bunch of easy options. Very simple, easy to understand steps. Now, I follow up with another prompt. None of my devices seem to be able to connect. This is now additional information that I've provided the chatbot, and the chatbot gives me a very reasonable response. So the issue seems to be with my internet service provider, and then it gives me some simple steps to check whether my internet is actually available. Now, let's configure a chatbot with a slightly different persona. It's still an assistant to help me with technology, but it's precise and a detail-oriented technical expert. And it's going to give me advanced and jargon-heavy solutions that are meant for experienced users who prefer technical depth. On line 12, I start the chat session with the model, and here is the same prompt as before. My computer is not connecting to the internet, and notice the jargon-heavy response. It talks about physical layer checks, cable integrity, modem router status, DNS server, IP configuration. This is definitely way beyond a novice user. Let's see what its response will be to my follow-up prompt. None of my devices seem to be able to connect. And again, we get a jargon-heavy response. ISP contact, router diagnostics, advanced network analysis if comfortable. Notice how a persona in the system instructions can completely change the voice of a model. Let's try a more light-hearted example. Here my system instruction tells the model that it's a cat whose name is Riku. And strangely enough, I'm going to ask this cat how to cook biryani properly. And the response you see is how the model imagines that the cat might respond. You can clearly see the haughty response that the cat provides. System instructions can be used to define the goals or rules for the task at hand. These goals or rules are used to guide the behavior of the model. I have a Python code generator here whose rules state that it should prioritize simplicity and readability, include detailed comments explaining each line of code, and structure the code to be beginner friendly with step-by-step logic. I've started a chat session. I'm now going to ask the model to write Python code to add two numbers. That's fairly simple code. Let's see what the model has to say. Notice that it defines the function, specifies a lot of comments. The function has documentation. Every line has a comment, and you can see that there are a number of example usages provided as well here at the bottom. This code is clearly meant for a beginner. Let's ask for another example. Write code to make a web request to a URL and parse the JSON response. And again, based on the rules that we've defined for this particular chatbot, we get very simple and easy to read code with an excessive number of comments, maybe a little too much. But as you know, this kind of code is great at a beginner level. Now, let's set up a model with slightly different rules and guidelines. The model is still a Python code generator, but it prioritizes performance and efficiency. Avoid comments unless absolutely necessary. Use concise variable names. And I've asked it to make use of advanced Python features like list comprehensions, decorators, and async programming. I've started the chat session. I'm going to pass in the same prompt as for the earlier chatbot. Please write code to add two numbers. And here is the very succinct and to the point response from the model. Notice the variable names are concise, there are no comments, they are clearly not needed for the simple function. Now let's try the second prompt. Write code to make a web request to a URL and pass the JSON response and observe the succinct response. Observe that it has an async function, fetch JSON. It makes of async IO HTTP client session. In the main function, it asynchronously fetches the JSON data. And you can see at the very bottom, we use async io.run to run the main function. Very precise and concise code with no comments and advanced Python features. You can use system instructions to define the output format that you want for the response from the model. I've instantiated a model here. Observe the system instruction on lines 3 through 7. The task is to generate responses in the JSON format. All responses should be valid JSON and they should be formatted for readability. And my prompt, give me some fictitious employee data for my task. On line 16, notice I call model.generateContent to use the Freeform mode. You could have chosen the chat mode if you wanted to. And here is the response from the model. Well structured, easy to read with the right indentation JSON. Now, you may still want the response in the JSON format, but with different constraints or different rules. Observe my system instruction here. Generate JSON with minimal white space and no pretty printing, suitable for transmission over the network. My prompt is exactly the same as before, fictitious employee data, just 3-4 records, and I use the freeform mode on line 16. Let's take a look at the response. Notice the JSON is now in a very compressed format with no extra white space. Hard to read, but perfect for transmitting over a network. You can have the model generate responses in any format you're interested in. CSV format, Markdown, anything. Here is an example system instruction on lines 3 through 13, asking the model to generate responses using raw Markdown. My prompt asks for a list of programming languages and their use cases, and I call model.generateContent. And notice the response is in the raw Markdown format. And of course, you can use IPython's Markdown object to convert the response to a readable HTML format. Here is another example of using system instructions to specify the output format of the model. I've set the model up to be a technical writer whose task is to generate responses in a simple, structured, plain text format using bullet points. My prompt is the same. I want a list of programming languages and their use cases, and I call model.generateContent to get the response from the model. And here is what the response looks like. Notice the simple language, the bullet points, and the markdown format. Let's get the output in a CSV format. For the same prompt as before, notice my system instruction on lines 3 through 6. Please generate all output in the CSV format for easy parsing. Make sure to include headers. The prompt is the same, list of programming languages and their use cases. Here is the response from the model, now in the CSV format. Notice that there are two columns, programming language and their use cases. System instructions can be used to define the output style and tone for the model as well. Here my system instruction asks the model to play the role of a content creator and always provide responses in a professional tone. My prompt is simple, benefits of cloud computing for businesses. Observe that the model gives a response as a technical writer and the tone is very, very professional. It talks about all of the different advantages to using cloud computing for businesses. Now let's tweak the system instruction a little bit. The model is still a content creator, but I've asked the model to provide answers that non-technical users are able to follow. So it's the tone that I want the model to change. The prompt is the same, benefits of cloud computing for businesses, but you can see that the response is very, very different. The model makes use of analogies. Cloud computing is like renting office space instead of owning a building, and it breaks down the bullet points in far more detail, and each bullet point is short and easy to read. Here is another change to the tone. Again, it's the same content creator, and I've asked the content creator to provide answers that appeal to financial decision makers. So now, when I ask about the benefits of cloud computing, there'll be a financial bent to the responses, and you can see that here in the generated text from the model. Observe that we have a section for financial advantages, and then we have a section for operational advantages and risk mitigation. This is what will appeal to financial decision makers. Let's try one last tone here. Here, I've asked the model to still be a content creator, but provide answers that fifth graders would follow. So, really make the answers very, very simple. The prompt is the same, benefits of cloud computing for businesses. And you can see the model's response is very, very simple and has a lot of schoolroom analogies. It's like having a magic backpack, it's super flexible, grows with you, saves money like a piggy bank. These were not terms used in the earlier responses. System instructions can also be used to provide additional context for any prompt that you send the model. Notice the system instruction in this example on lines 4 through 17. Observe that the system instruction is to create a job application cover letter with very specific details. Here is the prompt at the bottom where all of the details are provided, and when you just pass this prompt in without any additional information, the model uses the system instructions to generate the covering letter. The system instructions is what provides the additional context. With Gemini models, you can guarantee that a model's generated output always adheres to a specific schema so that you receive consistently formatted responses. This is especially useful if you have a set schema that you follow for other tasks. If you have the model generate its response using the same schema that you use for, say, data analysis or even machine learning, you can directly extract data from the model's output without any post-processing and feed that data to the other tasks that you've defined. This is control generation using Gemini models, and that's what we're going to look at next. Let's go ahead and import the libraries that we need. We'll use the JSON library to parse JSON. The generation config will allow us to control the schema of the generated output, the generative model, and part objects you've encountered before. Once again, we'll call vertexai.init to initialize our APIs to work with the specified project ID and location. Control generation is supported by Gemini 1.5 models, so you can use Gemini 1.5 Pro or Gemini 1.5 Flash. As we've discussed before, the Flash model uses Flash attention and is generally more performant and responsive. Instantiate the generative model. You can specify a response schema for the model if you want the model to generate output in a valid JSON format. And that's exactly what I've done here. This JSON response schema returns an array or list of JSON entities. Notice type is equal to array on line 2. The items in the list are all objects and they have exactly one property, brand name, which is of type string. On line 10, I've specified that brand name is the only required property that the entities in a list should have. Next, I'll specify this response schema while generating a response from the model. I use model.generateContent, so this is in freeform mode. The first input on line 3 is the prompt. I'm considering buying a car. Could you suggest a few? And the generation config input argument allows me to configure the structure of the response. I've set the response MIME type to be application/JSON. That's the structure of the response, and the response schema is set to the response schema that we saw previously. Let's take a look at the response from the model. We make the API call, and here the text field contains the JSON response. We have 4 brand names: Toyota, Honda, Mazda, and Subaru. The other details here include the metadata that's returned with the response. Observe that we have safety ratings across all 4 categories. We are interested in the response text, so let me just print that out. That's in the JSON format, and you can see the brand name property is present in each entity in the output list. Let's display this JSON in a nice indented format. I use json.loads. This parses the JSON and converts this to a list of Python dictionary objects, and then json.dumps converts the list of Python dictionaries back into a JSON string with the indentation that we have specified. And here you can see the list of 4 entities that was returned by the model in a nice indented JSON format. In my next prompt, I'm going to ask the model for some book details, and here is the response schema I want for the response that the model generates. So the type of the response should be array, that is a list of JSON entities. That's the type array on line 2. The items in the array are all objects. That's the type object on line 4. Every entity in the JSON list contains title, author, and genre of type string and a publication year of type integer. In addition, there is a nested character array for each book entity defining the characters in that book. The character array is defined on lines 10 through 21. Each item in the character array is a JSON entity with the properties name, age, and role of type string, integer, and string respectively. Name and role are required properties for each character, and title, author, genre, and publication year are required properties for the book details. Now, this is the schema in which I want the model to generate responses. Here is my prompt. Please give me the details of the book, The Adventures of Sherlock Holmes. I call model.generateContent, pass in the prompt, and within the generation config, I specify the MIME type as JSON and the response schema in which I want the response. On lines 12 and 14, I parse the JSON response from the model and print it out in a nice indented format. Let's see what the model has to say. And here is the result. Observe that it adheres strictly to the schema that we had specified as a part of the generation config. In addition to the title, author, genre, and publication year, we have an array of the 3 most important characters in the book. Here is another prompt that I sent to the model, and I want the response in the same format as before. I want the details of the book, Journey to the Center of the Earth, and I'm asking the model to assume that the characters are unknown, so it should not return any characters in its response. Once again, I specify the generation config with the response schema as before. Let's see what the model has to say here, and observe that it gives me the other information, but the character array is empty because I asked the model to assume that the characters were unknown. Let's try one more example with the same response schema before we move on. I want the details of the book, The Count of Monte Cristo. The rest of the code here is the same code that we've seen earlier. This particular book has many important characters, and you can see that all of these characters along with their age and role are listed out here. The properties in the JSON entities that are returned in the responses need not just be primitive properties such as strings, integers, and so on. You can also specify that you want your responses as an enum, one of a predefined set of values. Here is a simple response schema that will return a single enum value in the response. Type is string, and here is the enumeration. The possible values in the response are vegetarian, vegan, gluten-free, paleo, and keto. I'm going to use this response schema to categorize some food. This is useful if you want your model to perform a classification task where the input needs to be classified into one of a predefined set of categories. We'll use the prompt to define the actual dish. This dish consists of roasted vegetables, quinoa, and a tangy lemon dressing. It's a wholesome meal that can cater to various dietary preferences. I call model.generateContent. I set the response MIME type to be text/x.enum, indicating that I'm expecting an enumeration in the response, and I set the response schema. Here is what the response looks like. Notice the text says vegetarian. This is a vegetarian dish. And of course, you can print out just the response text that will contain the single value of the enum, vegetarian. Here is another input text to the model with the same response schema where we want the output to be of type enum. The dish is grilled chicken, sauteed spinach. And the response schema is the same as before. And you can see that this has been categorized as paleo. Here is another example of how you can use the Gemini model for a classification task and get the result in a strict enum format. The response schema is an enum where the possible values are dessert, main course, and appetizer. The prompt on lines 3 to 7 defines a culinary dish and it talks about chocolate cake, whipped cream, and so on. Observe the generation config specifies the response MIME type as enum, and this is the response schema we pass in. And in the response, you can see that the model has correctly identified this dish as dessert. It's just easier to see the model's response without the metadata, so I'll just print out the response text. And this, of course, gives us what we expect, dessert. Let's try this with one more dish before we move on to other examples of control generation. The prompt is a detailed description of a tender roasted salmon fillet. Again, we use the generation config where we expect an enum in the response and we'll print out the response text, and the model has correctly identified this as a main course. If you plan to use your model for classification problems such as sentiment analysis or product categorization, you might want to use this enum response format in order to get the results from the model in the form of classes or categories. In this demo, we'll continue working with controlled generation by specifying a response schema for the model responses. However, we'll apply it to a different use case. Control generation is very useful if you have information in an unstructured text format and you'd like that same information to be present in a structured JSON format. You can pass in the input unstructured text to the model and get a nice valid JSON in the response. That's what we're going to look at next. Let's say you have an alerting system that sends you messages about your server's health, and it sends these messages in the form of natural language. Maybe these messages are sent via email. Maybe you'd like to get these messages in a structured JSON format so that you can visualize this information in some kind of monitoring dashboard. That's what we try to do here in this example. Here is my server health response schema. Notice that it returns an array of JSON entities. Type is array on line 2. Since you can have multiple servers that you're monitoring, every entity in the JSON list or array that's returned corresponds to a particular server. That's why the items in the list are of type object. And let's look at the properties for each object. We have a timestamp of type string, CPU usage, that is a number. This is the percentage of CPU that the server has used. We have memory usage as a number. This is the memory usage expressed as a percentage. We have disk usage as a number, again disk use as a percentage. And then we have a status enum corresponding to each server. The status can be OK, warning, or critical. And here in the required field on lines 26 through 32, I've specified all of these properties as required properties in the JSON response. I have a prompt here that defines my server's health using natural language. And I ask the model to give me a quick status of the health of the servers I'm running. I have 3 servers and I believe one of them is not responding at all. Another one seems to have intermittent issues. I call model.generateContent. The generation config says the response MIME type is application JSON, and I pass in the server health schema that we had configured earlier. And on lines 14 and 16, I print out the JSON in a nice indented format. And here we see the status of the 3 servers. The timestamp, CPU usage, memory usage, and disk usage are all made up by the model. But notice that the status enum is accurate based on my input prompt. One server has a status OK, another server has a status warning, that's the intermittent issues, and the third server has a status of critical because it's not responding at all. Let's try this once again with a different prompt. Again, I want a quick status of the health of the servers. I have 2 servers and I think one is running out of disk space and the other is using a lot of memory. We'll use the same response schema as before, the server health schema. Let's see what the model has to say about this. Observe that we get a list of 2 JSON entities. The memory usage for the first server is at 80% and its disk usage is at 95% and its status says warning. The second server seems to be okay. The next example we'll see will also extract structured content from basically semi-structured data. And a great example of semi-structured data that you're likely to encounter in the real world is basically the logs generated by your website or application. Now here, before we look at the schema, let's take a look at the prompt on lines 17 through 23. The prompt passes in a number of different log messages. Every log message has a timestamp. It has a log level warning, debug, or info. And then there is some text which is essentially almost freeform in its nature. You can see the warning can be high memory usage. There is a warning for low disk space. There is info, system maintenance completed, debug, process started. Observe that this is not completely unstructured. Each time we have a warning log message, we have a corresponding warning code that can be useful. Let's set up a response schema to extract this information from our log messages. The response schema is defined on lines 1 through 15. I'd like the model to return an array of JSON objects, one object corresponding to each log message. So type on line 2 is an array, that's the return type of the entire response. Every item in the array that's returned is of type object. You can see that on line 4. Now the properties of the object include timestamp of type string, logging level of type integer. So those warning, info, and debug levels will have to be converted to integers. Then we have the actual message itself of type string. And in addition, the JSON entity could contain memory usage and disk space of type integer and a warning code of type string. Now, memory usage, disk space, and warning code may not be present in every log message, and that's why I've set nullable to true for those properties. And if you look at the required field on line 13, I've set timestamp, logging level, and message as required. The other properties are optional. We are going to have our log messages parsed into this response schema. I call model.generateContent. I have my generation config that specifies this response schema. And on lines 32 and 34, I pretty print the JSON response from the model. Let's run this and take a look. And you can see that the model does a great job of parsing my log messages. Notice the first JSON entity. You can see logging level is 1, that's for warning. You can see the message, high memory usage detected, 85% used. Memory usage is 85 and the warning code is 1001. The third entity, this is the info log with logging level 0 and the message simply says system maintenance completed and it doesn't have values for the other properties. If you scroll to the bottom, you can see that the last entity is another warning with logging level 1. The message is about a system running low on resources. Notice that we have memory usage at 90, disk space at 2 for 2 GB, and the warning code is 2050. Now, the next example that we'll look at is how we can extract sentiment and other details from unstructured user reviews. Let's look at the response schema first on lines 1 through 16. We've asked the model to return an array of JSON objects. Every JSON object in the response should contain a rating of type integer, the name of the dish of type string, an enum value of sentiment, which can be either positive, negative, or neutral, and an explanation for why exactly this particular sentiment was extracted from the review. Let's take a look at some example food reviews here in my prompt. My prompt says, analyze the following restaurant dish reviews, classify the sentiment, and provide an explanation for each sentiment. Notice that each review contains the actual text of the review, the rating, and the dish that the review refers to. The code on lines 34 to 43 to query the model and print out the JSON response, you've seen that before. Let's run this and see the response from the model. The model has done a perfect job of extracting the information in the JSON format. For example, for the last dish that you see here on screen, the dim sum, the sentiment is neutral, the rating is 3, and the explanation has the text of the review explaining why this particular sentiment was extracted and why this particular rating was given. Now, this last example for control generation is going to be a fairly complex one. Once again, we'll use the response schema to extract structured information from natural language text. What's complex here is the actual response schema. I've specified a number of constraints for the different properties that the model should adhere to in the JSON that it generates. The response schema is a list of JSON entities as before. It has a title, user profiles, and a description. This is the schema representing a list of user profiles with personal information and hobbies. Let's look at the structure of the JSON objects in the array that's returned. Every JSON object has the following properties. A user ID that is of type string. Notice that I've specified a description for this property as well as an example user ID. I then have the name property of type string. The minimum length of the name is 5 characters, and I've specified an example and description as well. User profiles will have an age property of type integer. The minimum value for age is 0 and the maximum is 120. User profiles can have an email property of type string. When you specify the format as email, the model will ensure that what is returned in this field is a valid email address. We then have the hobbies for the individual defined on lines 32 through 43. This is a nested array. The items in the array defined on lines 35 through 39 are of type string and have a minimum length of 1. An example is photography, that's a hobby. On lines 40 and 41, I have specified some constraints for the hobby array itself. It should have a minimum of 0 items and max items is 2. And then we have a Boolean value profile complete. Type is Boolean. The default value for this Boolean is false. Not all of these properties are required. I've specified the required properties on line 51, and I've also specified the order of the properties within the JSON object. That is the property ordering field. First should be user ID, then name, then profile complete. The other properties, well, I don't really care about their order. Now let's use this response schema in order to parse information from some natural language text. The prompt that I've specified on lines 1 through 16 talks about 5 different individuals, and it contains personal information about each of these individuals, including some of their hobbies. For Jane Smith, we have no age or email address, but she loves painting and cooking. Mike Davis is 41 years old, who enjoys climbing, hiking, surfing, and kayaking. So Mike has more than 2 hobbies. Let's extract structured data from this text and see what the model's response looks like. Notice that for all entities, the user ID field comes first, then name, then profile complete. That's the property order that I had specified. Age, email, and hobbies have been extracted correctly for each individual. For Jane Smith, notice that we have no email address and age is set to 0. If you scroll down and take a look at Mike Davis, notice that only 2 out of 4 of his hobbies have been listed here. That's because we had specified max items as 2 for the hobbies array. I'm going to use the same response schema to extract structured information, but I've modified the prompt a bit. Alex Johnson is now aged 135, beyond our max age limit of 120. You'll now see that Alex Johnson's age in the response has been set to 13. The model has truncated the age value extracted so that it fits within the constraints that we had specified in our schema. JSON schemas can be arbitrarily complex and can indicate many nuances in your structured data. I'll show you one such nuance in this last example. Here we are returning an array of student entities. That's what this schema specifies. Every student has the following properties: student ID of type string, name of type string with a min length of 1, and contact information. Notice that I use the any of property in the response schema, indicating that the contact information can be an email address or just a simple string. So if a student has a valid email address, that will be extracted, or if the student has a phone number or an address, that may be extracted as well. So the contact information is any of these formats. Let's take a look at a sample prompt and the information extracted by the model. Here I have descriptions for 3 different students. Alice Johnson has an email address, alicejohnson@example.com. Bob Smith has a phone number. You can see the phone number on line 12, while Charlie Brown prefers to be contacted on X, formerly Twitter. You can see his Twitter handle on line 19 at Charlie Brown. Let's see if the model is able to extract the right information from this prompt. Student ID and name extracted perfectly, and notice the contact information can be an email address, a phone number, or the Twitter handle at Charlie Brown. In the demos that follow, we'll be working with text generation using Gemini models. But before we get to that, I want you to get a little bit of an understanding of how text generation works in LLMs. This is true for all large language models and not just the Gemini models on Vertex AI. Now we know how to interact with model. You send a prompt to the model looks at your prompt, understands it, and sends back a response. The model's response is in natural language. That is, it is a sequence of words that makes up a sentence or multiple sentences. So this is what the response from a model might look like. You can use Python for programming. Notice that this response is a sequence of words, and the way large language models work is that the model generates one word at a time. So just an asterisk here, models actually generate one token at a time, and tokens don't exactly correspond to words. You can think of a token as a partial word or a subword. But for the sake of simplicity and for understanding how LLMs work, let's assume that the model generates one word at a time. Now, at every step in the generation process, there can be many possible next words that the model can choose from. So here is the example of the generation process at one particular step. So the words you can use have already been generated, and now the model is trying to figure out what the next word should be. The model will produce a number of different words that it can choose from. So it will produce all of these words that you see here as an example, a hypothetical example. Python, Java, C++, C#, Lisp, English, French. Each of these words is associated with a probability score. So when the model looks at all possible next words, it knows that there are probabilities associated with each possible next word given the current context. So maybe given the current context, Python has a probability of 0.4 or 40%. Java has a probability of 0.3 or 30%, C++ 0.1, 10%, C# is 0.08 or 8%, Lisp 5%, English 4%, and French is 3%. All of these probabilities add up to 1. While generating the output sequence, the model has to pick one word from all of these possible next words in the sequence. Now, since each word is assigned a probability, the model picks one word from the possible next words based on the probability scores. This means that words that have higher probability scores tend to be more likely to be picked. For example, there is a 40% chance that the next word picked will be Python, 30% that it will be Java, and a 5% chance that the next word picked will be Lisp. So higher probability words are more likely to be picked, and how exactly the model chooses which word should be picked at the next step in the generation of a response, well, that is something that you can control using several parameters. If the decoding strategy that the model uses is greedy decoding, it will always pick the word with the highest probability score. Or it could pick a word at random with higher probability words more likely to be picked. This is the decoding strategy of the model and something that you can configure as we'll discuss in just a bit. The model generates its final response by picking words at each step. So at each step, it has a number of words with probabilities and it will pick a word at each step to give you the final response. Now, you can use model settings or model parameters to tweak the generated text. Large language models offer settings that you can tweak to make the generated text more creative and diverse or more predictable and deterministic. If you're using your model for factual responses, you might want it to be predictable and deterministic. If you're using your model in creative contexts, such as writing poetry or generating vivid descriptions, you want the model to be more creative. So there is a trade-off that you have to make when working with language models: creativity versus predictability. High creativity will produce more diverse and unexpected results, making the text more interesting and engaging to read. On the other side, If you tweak your model to produce more predictable and deterministic response, your responses will be more consistent and will contain more reliable text. Very useful when you need precise answers to your questions. You can use model settings to control the creativity and predictability of the models. So, based on where exactly you're integrating text generation with LLMs, you could have your model be more creative or more predictable. Striking a balance can produce text that is both interesting and coherent. Different models offer different settings to control creativity and predictivity of the models. Here I'm going to discuss two important settings related to Gemini models. The first is temperature, and the second is top P sampling or nucleus sampling. Let's first understand how the temperature parameter works. The temperature parameter for Gemini models ranges between 0 and 2. Both values are inclusive. Lower values are closer to 0 and higher values are closer to 2. Higher values closer to 2 result in more creative and diverse output from the model. The model will produce text that is more vivid and more engaging in nature. On the other hand, lower values of temperature closer to 0 result in more predictable and deterministic output. The model may use more mundane words to describe information, but the response from the model is likely to be the same when you pass in the same prompt. Let's understand the role of this temperature parameter by going back to how text is generated using LLMs. At every step, the model has a number of words that it can choose from. Each word is assigned a probability, and the model picks one word from this probable set of words. Let's visualize this. I'm going to map out the original probabilities of the possible next words that the model could choose from. So Python at 0.4 has the highest bar, French at 3% or 0.03 has the lowest bar. The temperature parameter adjusts the randomness of a language model's output by scaling the probabilities of these token or word predictions. A higher value of temperature tends to flatten the probability distribution, making less probable tokens more likely to be chosen. Notice that by flattening the probability distribution, the probabilities of words like Python, Java, and C++, which are high probability words, have become lower, and the probabilities of words such as Lisp, English, and French have become higher. Thus, a higher temperature makes less probable words such as Lisp, English, and French more likely to be chosen. Let's go back to the original probability distribution across the possible next words, and let's talk about the effects of lower values of temperature. A lower temperature sharpens the probability distribution over the next possible set of words, favoring the more likely tokens. Notice that the probability values associated with Python, Java, and C++ have gone up, and the probabilities associated with Lisp, English, and French go down. This makes words like Python, Java, and C++, which already have a high probability, more likely to be chosen. Now that we've understood how temperature works, let's move on to another parameter to control creativity: top P sampling or nucleus sampling. Values for the top P parameter range between 0 and 1, both inclusive. This top P value is a dynamic cutoff threshold. Top P parameter controls diversity by dynamically selecting the smallest subset of tokens whose cumulative probability exceeds the threshold P. Higher top P values, such as values close to 1, 0.9, or 0.95, allow for more diverse outputs by including a broader range of words or tokens to choose from. Lower values of top P, such as values close to 0, maybe even 0.3 or 0.4, restrict the output to highly probable tokens for more focused and deterministic results. The top P parameter, also known as nucleus sampling, works by selecting the smallest set of top candidate words, that is, words with the highest probability score whose cumulative probability exceeds a given threshold, and that's the threshold we specify P. Let's understand how this works by going back to our probability distribution of the possible next words to generate in the sequence. Let's say these are the possible words and their corresponding probabilities. Notice that the sum of the probabilities of all of the individual words sum to 1. Now sort all of the words in order of probability. Since they are already in the order of probability, this sorting works just fine. Now let's say the value of top P that we have specified is 0.5, that is the threshold for cutoff. The text generation algorithm will sum up the probabilities of the words starting with the highest probability word, and it will choose the smallest subset of words that exceeds this cumulative probability threshold. So the subset of words that includes Python and Java is 0.4 plus 0.3 equal to 0.7, which exceeds the probability threshold of 0.5. The model will then select the next word only from these two words. Either Python or Java will be chosen. Now let's say you increase the top P threshold to be 0.7, then one more word can be included in the set of possible words to choose from. The cumulative probability here is 0.4 plus 0.3 plus 0.1 equal to 0.8, which exceeds the top P threshold of 0.7. Higher the value of top P, more words to choose from, and more diversity in the output generated by the model. The highest possible value for top P is 1. This is where the model can pick from all possible words, giving you the greatest possible diversity in the output. In this demo, we'll see how you can tweak and control the response generated by a model by specifying model parameters. These are sampling parameters that you can set in a request to the model. We'll explore parameters that will have the model generate more creative or more deterministic outputs, control the length of the response from the model, and so on. Now, I'm going to install a library that we'll be using in this demo. This library is called Rouge Score. Rouge Score, where Rouge is an acronym that stands for Recall-Oriented Understudy for Gisting Evaluation, is a metric used to evaluate the quality of generated text by comparing it to a reference text. Rouge Scores evaluates the generated text by using overlapping n-grams, longest common subsequences, or word pairs. We'll use this to compare how similar generated responses are from a model. So go ahead and install the Rouge Score library. Next, we'll set up the imports that we need for this demo. Many of these we've worked with before, others I'll explain as and when we use them. Let's initialize our Python client by calling vertexai.init and specifying the project ID and location. Now, one of the parameters that you can tweak for a model is the type of the response. Now, the model that I've chosen here is the Gemini 1.5 Pro 001 model, and here is my user prompt. Explain the concept of artificial intelligence, and I want the model to provide a definition, examples of AI applications, and advantages of using AI. Now, let's call model.generateContent, pass in this user prompt, and in the generation config, I specify the response MIME type as text/plain. The model should give me its response in the plain text markdown format, and you can see that it does. I'm now going to send the same user prompt as before, but in the generation config, I've specified the response MIME type as application/JSON. And now the model gives me its response in the JSON format. The response MIME type is a parameter that you can configure to change the structure of the model's response. I'm going to be exploring a number of different parameters to tweak and tune the response from the model. So I'm going to set up a helper function for this, generate content with params. This takes in the model as an input argument, the user prompt, the response MIME type, which is set to text/plain by default, the max output tokens that is set to 300 by default. This is what will be used to control the length of the model's response. The temperature is set to 1 by default. We've discussed the temperature parameter earlier in this learning path. This controls the randomness of the model's responses. A higher value of temperature produces more creative and diverse responses from the model, while a lower value of temperature makes the output more focused and deterministic. The top P and the top K parameters are also used to control the diversity of the response from the model. I'll explain how those parameters work when we actually use those parameters. The seed parameter allows us to get more deterministic responses from the model, and the stop sequences are predefined strings which, when they appear in the generated text, causes the model to stop generating output. All of these input arguments can be configured using the generation config. And you can see that I instantiate this on lines 14 through 22. I call model.generateContent, pass in the user prompt and the generation config, and return the response from the model. Next, I'm going to set up a helper function that will allow me to compare two responses from the model. Compare responses takes in the previous response and the current response and will show me in a visual way how similar they are. The differ object from Python's difflib module, which I instantiate on line 3, provides tools for comparing sequences. On line 5, I split the model's responses into sentences and I compare the individual sentences. On lines 9 through 20, I display a table with the individual sentences from the two responses. The diff variable contains a line-by-line difference between the two responses. And on lines 9 through 20, I display this difference in the form of a table. Sentences in red are removed sentences, that is, they've been removed from the previous response and are not present in the response. Sentences in green are for added sentences, that is, these are new sentences that are present in the response but were not present in the previous response. And sentences in black are the sentences in common between the previous response and the current response. And we'll display this table in a nice HTML format. Now let's generate some text using the model with temperature set to 0. With temperature 0, the model is at its most deterministic. The user prompt asks the model to picture a perfect summer day at the beach and asks for a description that flows smoothly with no repetitive details in 3 short paragraphs. Now the temperature is 0 and I call generate content with params with this value of temperature. I get the response from the model and print out the text of the response on line 17. Let's go ahead and run this, and here is the response from the model. It's a pretty detailed and vivid description, but a higher temperature value will definitely improve this. Now a temperature of 0 produces more deterministic responses, so what I'm going to do is generate a second response with the same temperature value equal to 0. Let's see how much difference there is between the first response and this second response. Here is the second response. It seems fairly different to me. Let's compare the responses in a visual format. I call compare responses, and you can see even with temperature 0, the responses are fairly different. Generative models are not fully deterministic. You're making the model more deterministic by setting temperature to 0, but it's unlikely that you'll get the exact same output each time, even if your prompt is exactly the same. Let's go to the other extreme. Let's have the model be at its most creative. I've set the temperature parameter to be equal to 2. And the prompt is the same. Picture the perfect summer day at the beach. Let's take a look at the response from the model. The response seems very vivid and descriptive. Now let's use temperature equal to 2 and generate yet another response from the model. This is the second response. And you can see the response looks very different. Let's compare the two responses, the previous response and the current response, and you can see that they are very, very different. Their lengths are different. Every sentence is different. With temperature set to 2, the model content will be the most diverse. So you're unlikely to get the same sentences in the response when you ask the same prompt of the model. Next, we'll explore the top P parameter for the model. Top P is also known as nucleus sampling, and it controls the diversity of a model's output by limiting the choice of tokens that the model can pick to the smallest subset whose cumulative probability exceeds the threshold that we specify. Now, when you set top P equal to 0, this means that nucleus sampling is effectively disabled, which means as it's generating tokens for the response, the model will always pick the highest probability token at every step. Here in the user prompt, I've asked the model to generate a blurb for a murder mystery set in a village. Top P I've set to 0. I've used the Gemini 1.5 Flash model. I pass in this top P value to generate content with params, and I print out the text of the response. This should be the model at its most deterministic. And here is what the first response looks like. Now, keeping this top P value of 0, let me generate a second response from the model. And it seems to me that the second response is very similar to the first. let's use the compare responses function to compare these two responses, and we'll see how much the text overlaps. And it's pretty clear that when we set top P to 0, when the model generates the response text, it always picks the highest probability word, which means that the response is fairly deterministic. The first three sentences in black, those are sentences that are present in both of the responses that we generated from the model. Willow Creek is the same in both, the same setting. The detective Amelia Thorne is the same in both. I'm now going to set the top P value to be 0.5. This means the model will consider only the smallest subset of tokens whose cumulative probability adds up to 50%. So at every step in the generation of all the possible tokens that can be picked, the model will only select from those tokens where the cumulative probability is 0.5 or 50%. This will make the model more diverse and less deterministic than with top P equal to 0. Here is the first response. Let me go ahead and generate the second one. I've set top P equal to 0.5 once again. Here is the second response. Let's use compare responses to see how similar these two responses are. You can see there's exactly one overlapping sentence in the two responses, the first one in black, and the remaining sentences are all very different. The default value for top P is set to 1. So when we used models without specifying a value for top P, it used the default of 1. Now let's look at another parameter, top K. Now the top K parameter is not supported by all models. It's only supported by the Gemini 1.0 Pro Vision model, and that's the model that I have used in this example. Top K is another parameter that controls the diversity of a model's output by limiting token selection to the top K most probable tokens at each step of text generation. So while the model is generating text, instead of considering all possible tokens, the model will randomly sample from only the K highest probability tokens. The default value of top K is 32. If you use a top K value of 1, the model will select the single most probable token. That's referred to as greedy decoding. If you use a top K value of say 5, the model randomly chooses from the 5 most likely tokens, introducing some variability in the response. Here I've chosen a top K value of 3. So the model's response will have some diversity but not very much, because at each step the model just has 3 tokens to choose from for text generation. Let's see what the response looks like. Here is a blurb for a legal thriller novel. Let me get a second response with the same top K value of 3. Here is what the second response looks like. I'm now going to use compare responses to compare the two responses. And you can see that in my case, even with a small value of top K, just 3, the two outputs are very different. Now let's try with a larger top K value. I've set top K to 40. I use the same 1.0 Pro Vision model, and here is the response from the model. Again, it's a blurb for a legal thriller. Top K of 40 allows the model 40 possible next tokens to choose from. So the model should have a more creative and diverse output. Here is the second response from the model with top K set to 40. And you can see this response is very different from the first. And we can verify this by calling compare responses. And notice all of the red and the green, the two responses are very, very different. Rather than comparing responses visually as we've been doing so far, you can see how similar two responses are by computing the Rouge score. The Rouge score measures the overlap between two responses, and it's typically used to compare generated text and some reference text. The Rouge score calculates metrics such as recall, precision, and F1 score. I'll explain what these mean in the context of comparing text in just a bit. Let's go ahead and initialize the Rouge scorer, and I've asked it to compute metrics for 3 different Rouge scores: Rouge 1, Rouge 2, and Rouge L. Rouge N scores compares n-grams, either unigrams or bigrams, between the two texts. For example, the Rouge 1 score that we'll compute will calculate how many overlapping unigrams exist between the two texts. Unigrams are single words. The Rouge 2 score will compare bigrams between the two pieces of text. Bigrams are words that appear together consecutively. Rouge L scores measure the longest common subsequence LCS between the two pieces of text that you are comparing. This accounts for sentence structure and order in the two text. When you set use stemmer to true, the Rouge scorer will reduce the individual words to the base or root form by removing suffixes or prefixes. This will standardize words like swimming to its root form swim. Let's now compute the Rouge score for a few different pairs of sentences. Here, my reference text and the predicted text are exactly the same. Notice there is no difference between the sentences. On line 4, I pass these two into scorer.score, and on line 6 through 10, I print out the precision, recall, and F1 score for the text pair that I'm comparing. Now, you shouldn't be surprised to see that precision, recall, and F1 score for Rouge 1, Rouge 2, and Rouge L are all the same, equal to 1. Precision measures the fraction of overlapping n-grams in the generated or predicted text compared to the total n-grams in the generated or predicted text. Recall measures the fraction of overlapping n-grams in the generated text compared to the total n-grams in the reference text. The F1 score balances precision and recall by calculating their harmonic mean to provide a single performance metric. Now, in my next example here, the reference text is a little different from the predicted text. The two pieces of text are not that different. The term lived up to its reviews exists in both, but the initial part of each sentence is different. I'll now compute the Rouge score for this predicted versus reference text. And you can see that the Rouge scores, while high, are not 1. If you were to just look at the overlapping unigrams, that is the Rouge 1 score, precision is 0.9, recall 0.83, and the F1 score is 0.869. Now, in this third example, my reference text and predicted text are both very different. The meaning overall is the same. Both sentences still praise the book, but they use very different words. Remember, Rouge scores are comparing the words in the two texts, and here you can see that the precision, recall, and F1 scores are very low. There is very little overlap of unigrams, bigrams, or longest common subsequence between the two texts. In order to get the most deterministic responses from the model, you can set the seed parameter. When the seed is fixed to a specific value, the model makes a best effort to provide the same response for repeated requests. But you should know that a deterministic output is not guaranteed. And if you change parameter settings such as the temperature or the top P or the top K, that can cause variations in the response even when you use the same seed value. Here, when I call generate content with params, I've used the default values for temperature, top P, and top K, but I set the seed to a specific value 1, 2, 3, 4, 5. Now, let's generate the first response from the model. Then I'll generate a second response and we'll compare. Here is a blurb for a dramatic novel that spans generations. Now I'm going to use the same prompt as before with the same seed. So the user prompt is still a blurb for a dramatic novel spanning generations. The seed is still 1, 2, 3, 4, 5. We are using the default values for temperature and top P, and these default values set up a balance of creativity and determinism. And here is the second response. I feel like it's close to, but not really the same as the first. Let's call compare responses to compare the first response with the second response. And you can see some similarity, but some differences as well. So the output was not really very deterministic. Now, the real test is when we compute the Rouge score of the first response and the second response. This will give us an indication of how different or similar the two responses are. And if you look at the precision, recall, and F1 scores, you can see that they are somewhat similar, but not really very similar. For the Gemini 1.5 Flash model, temperature has a default value of 1 and top P has a default value of 0.95. So there is some diversity and creativity in the output of the model, even when we use the same seed. So the same prompt need not produce a deterministic response each time. Now let's set all of the possible parameters to the lowest possible value. We have the same user prompt as before. I use the Gemini 1.5 flash model. Seed is 12345. Temperature is at its most deterministic 0. And I've set the top P to a very, very small value 0.1. Now, this model does not take into account the top K parameter, so I've left that as is. The temperature and top P parameters are set such that the model is as deterministic as possible. Let's take a look at the response from the model. Keep in mind the basic structure of this text here. We'll see how similar the text is when we try to generate the response once again. I use the same parameters as before. Make sure the seed is the same, 1, 2, 3, 4, 5. Again, we keep the model very, very deterministic. Temperature 0, top P 0.1. And here is the response. And if I'm not mistaken, it seems identical to the previous response. Well, we'll only know when we actually compare these two responses. So I call compare responses with the first response and the second. Notice no differences were found. The two responses are identical because they have the same seed and because we set the other parameters to their most deterministic values. Let's verify this once again by computing the Rouge score, precision, recall, and F1 scores for all Rouge metrics, a perfect one. The next set of model parameters that we'll explore are stopping parameters. These can be used to stop the generation of text. The first is the max output tokens, and I've set it to 100 in this example. My prompt asks the model to explain how to prepare a classic French omelette. Because we've set output to 100 tokens and we know that one token is about 4 characters, notice that the model's response is truncated. Once we get to about 100 characters, the model just stops generating text. Let's specify a larger token limit. Here I've set the maximum output tokens to be 1024. I have the same user prompt, the same model. And I call generate content with params as before. And this time when you look at the model's response, you can see the response is complete and rather long. So the 1024 tokens that we had specified as the token limit was sufficient for this response. Now I'm going to ask the model to generate some HTML, an example of how to create a simple HTML form with input fields and a submit button. I haven't explicitly specified a token limit here in my generate content with params, but in the default values that I pass as an input argument to the model, I've set the token limit to 300. You can see that early on when we define this function. Now, this particular token limit causes the model's response to be truncated. Right in the middle of the screen, you can see the opening HTML and the closing HTML for the form. That is form and /form within angular brackets. And you can see that the explanation is truncated because of our 300 token limit. Never mind that. Now let's see how we can configure stop sequences to stop the model from generating content whenever a stop sequence is encountered. Here I've set a single stop sequence, the closing HTML tag for the form. This is on line 6. When I call generate content with params, I pass in the stop sequences on line 14. Let's see what the response from the model looks like. Notice we have the opening HTML tag for the form, that is form in angular brackets, but we do not have the closing tag. That was a stop sequence. The moment that was encountered, the model stopped generating text. Now in our very last example here, I'll show you how you can configure the safety settings for your model. The Gemini model has 4 possible harm categories and you can specify a harm block threshold for each. Here are the 4 categories and the thresholds that I have specified. I have the harm category hate speech on line 3, on line 7, the category dangerous content on line 11, sexually explicit, and on line 15, harassment. I've set different harm block thresholds for each of these. On line 4, I have the block medium and above for hate speech. On line 8, I have block low and above for dangerous content. On line 12, I have block only high for sexually explicit, and I have block none for the harassment category. Each category is configured using a safety setting object. I have 4 safety setting objects in a list. Now let's see how we can specify these safety settings when we generate the model's response. I instantiate the generative model on lines 3 through 6. I've set the model name and I set the safety settings to the list of safety setting objects. And then I use model.generate content to get a blurb for a dramatic novel spanning generations. Now, this response doesn't really demonstrate the safety settings in action. Gemini model responses tend to be safe overall. You'd have to try quite hard to jailbreak the model in order to produce these unsafe responses, but hopefully, the safety settings will help you there.